Hello everyone. This is continuation of our lecture 1 which we did last time, and here we'll start from the topics where we ended the lecture 1. If you haven't gone across lecture 1, please find some time and do go through. So I'll start with the problems I gave you to solve in lecture 1. After that we'll move to the lecture 2 topics. So there were two problems which I gave yesterday in lecture 1. So first problem was something like there are three bodies having masses Ma, Mb and Mc. So what happens is these three interacts with each other by some means, and what happens is now A develops a positive charge, B is still neutral, and C develops a negative charge. So question was, what is the logical uh, uh, comparison between Ma, Mb and Mc, right? So this is a very simple and direct question. What happens is, as I said, any bodies develop charge either by gaining electron or losing electron. So in this process, what has happened is C has got negative charge, which means C has got an electron, and A has developed a positive charge, which means A has lost some electrons. So A has given electrons, C has got some electrons, and B is still neutral on its older mass. So you know that electron has a mass associated with it. The mass of electron, it is 9.1 into 10 to the power minus 31 kg. So electron has a mass associated with it. So since C has gained some electrons, C will become heavier. B is still at its original mass, and A, since it has lost electrons, A will become lighter than its previous mass, and hence this will be the logical expression, which will be a comparison of Ma, Mb and Mc. Yeah. So second problem was how many number of electrons are in 1 Coulomb charge. So this is again a very simple problem. So as I already discussed and said that charge on an electron, on one electron, is 1.6 into 10 to the power minus 19 Coulomb. So now I need to find out that in 1 Coulomb how many electrons will be there, right? So this is like unitary method problem. Like if cost of one banana is 10 rupees, so in 20 rupees how many banana you can buy, something like that kind of problem. So let me reverse it. So 1.6 into 10 to the power minus 19 Coulomb corresponds to 1 electron, right? So 1 Coulomb will correspond to 1 by 1.6 into 10 to the power minus 19 electrons, right? Now you can quickly solve and tell me what exactly is the answer. Let me just solve it for you. So something like this, 6.2 into 10 to the power 18 electrons. So in 1 Coulomb charge, you see that we have these many electrons. So 1 Coulomb itself is a big amount of charge, you can say. Okay, yeah. Okay, so we'll start with today's topics. So we said yesterday that there are two types of charges. One of them is positive and another is negative charge. We know that like charges repel each other, unlike charges attract each other. But now we need to identify, or we need to know that what exactly is the amount of force by which two charges are either attracting or repelling each other. So we don't have to worry a lot because Coulomb has done the job already for us. So we have a Coulomb's law for that. Coulomb's law of electrostatic force. So what Coulomb's law states that, let's say that we have two charges, 2 point charges. Let me not put a sign as of now. Let's say q1, like we denote charge by q. So let's say q1 is one charge, q2 is another charge, and it is separated by a distance, let's say d. So d is the distance between q1 and q2, right? So these two are point charges. Point charges basically means that distance between these two charges is very greater than the size of these charges. Like it would have some radius. Let's say r1 is the radius for this, but distance between these two charges is very greater than the radius of this particular body. So this is considered as a point charge. So now Coulomb's law states that force between these two, so let these are two charges, there will be a force between them. The force can be attractive or repulsive, that is not of the concern as of now. So Coulomb's law states that if F is the force between these two, the force between these two charges will be proportional to the product of their magnitude of charges. Okay, the first expression of Coulomb's law states that force between two charged bodies is proportional to product of their charges, magnitude of charges, and the force is also inversely proportional to square of distance between them, right? So these two are the expressions which comes out of Coulomb's law. Coulomb stated that the force between two charged bodies is directly proportional to product of their charges, and it is inversely proportional to square of distance between them. We can say that as greater is the magnitude of charge, as greater will be the force. As greater is the distance, as lesser will be the force. This is what we mean by the proportionality. So if I combine 1 and 2, I can say that the force between two charged bodies is proportional to product of their masses and inversely proportional to square of distance between them, right? So we know that when we remove proportionality, we need to put a constant. So we can say that force is given by k q1 q2 by d square. This is the expression of force. Okay, so here k is called as Coulomb's constant. Since it is experimented by Coulomb, it is called as Coulomb's constant, right? We will talk about what is the value of k and all that, but this is the expression of force. By this expression, we can easily calculate the force of attraction or repulsion between two charged bodies. So now here are some assumptions in Coulomb's law. Let me talk about that. So assumptions. So what exactly is Coulomb's law? We said that, yeah, there is a charge q plus q1, not ignore the plus, q1 q2 is separated by distance d. The force will be given by k q1 q2 by d square, right? So the statement of Coulomb's law states that the force between 2 point charges is proportional to the product of their magnitude of charge and inversely proportional to a square of distance between them. So Coulomb considered these charges are point charges. Charges should be point charges. So as I already explained, point charge means the distance between these two charges is very higher than the size of the charge, right? And second is a very generic assumption is charges should be at rest. Should be at rest. Because if charges go into motion, a lot of different kind of new forces would come into effect. So these two are assumption of Coulomb's law, right? So we just discussed about what is Coulomb's law and what is the expression of Coulomb's law. But let's get back into history and think how Coulomb would have come across this law. So the law states that force is proportional to product of magnitude of charges and inversely proportional to square of distance between them, right? So at that time, when Coulomb was doing the experiment, he had no means to measure the amount of charge. The magnitude of charge was unknown to him. What he had was a torsion balance, right? Torsion balance is a meter which indicates the force between two bodies. Like it would tell me if that what is the amount of force by which a body is attracting or repelling. So it would tell me the force magnitude. So this is the instrument which he had. But still, if I have the force, I have three more variables here. Let's say k is also not very uh, uh, k is a constant, but let's say that for that time when it was in descriptor, k was also a variable kind of thing. So we have three variables across this. So how would he would have connected these three variables is what we need to think, since he didn't know the charge and there was no way to measure the charge as well. So what he did is, let's say he took a sphere, a charged body, let's say plus q is the charge on a sphere, and he took an uncharged sphere, and these two spheres are of same size. So when he brought these two spheres in contact with each other, these two got equal amount of charges, right? So now he can bring these two closer and put an expression for force, right? So let's say that initially now it have got q by 2 q by 2. Now again I can bring a similar size sphere and distribute it to q by 4 q by 4, right? So in this expression, now what I can do is, let's say I have a charge q and q. I know the force. Let's say this is f q square by something like that, d1 square. Let's say something d1 square, right? Now uh, now let's say the charge is q by 2 and q by 2. Now again I know the force, so I can say that it is q square by 4 by d2 square, right? So now I am able to relate that, yes, how f is dependent on this k, how f is dependent on the distance, how f is dependent on the q. So now we know the expression, but at that time the mystery was to connect these these variables, like f is a variable, q is a variable, d is a variable. So based on the tabulation, like let's say there might be a tabulation between q and d, q q and d, and let's say that this is the force, right? So when q was kept same and distance was varied, the force would have a specific magnitude. When distance would have been kept same, the charges would have been varied, the force would have been a different magnitude. So after connecting all dots, the Coulomb came at this expression which says f equal to k q1 q2 by r square, right? So through this I wanted to make you understand on how can we come at this particular expression and how Coulomb would have approached, right? Yeah, so we just discussed about the Coulomb's law and the experiment which led to the discovery of Coulomb's law. Now we let's bring back the Coulomb's law and think about the constant. What exactly is the constant k? What exactly is Coulomb's constant? What is its value? What would be its unit? So let's talk about that. So the expression is f equal to k q1 q2 by d square. So k is a constant which we call as Coulomb's constant, right? So the measurements showed that the value of k is 9 into 10 to the power 9, right? And the unit will be Newton meter square per Coulomb square, right? You can just find it out that k is what, f into d square by q1 q2. Using this you can say the unit will be Newton meter square by per Coulomb square. So this is the value of k. What exactly is k? So the value of k is given by expression 1 by 4 pi epsilon naught, which in turns to 9 into 10 to the power 9 for vacuum, right? So now there is a twist here. The k would depend on the medium. Like if two charged bodies are placed in a vacuum and two charged bodies are placed in some other medium, let's say water or in a glass or somewhere else, the amount of the magnitude of force of attraction or repulsion between them would vary, and this k and this epsilon naught would differentiate that force. So this epsilon naught is for vacuum, and epsilon naught is called permittivity of free space. Permittivity of free space or permittivity of vacuum, right? and its value is something like 8.85 into 10 to the power minus 11 Coulomb square per Newton meter square. So we assumed that two charged bodies were placed in vacuum, and based on that the value of constant would be 9 into 10 to the power 9, which is the general case, and epsilon naught comes to be 8.85 into 10 to the power minus 11. Now we should think, what if these two charged bodies are placed in some different medium? There we need to place a variable for that as well, right? Okay. So generally talking, let's say that F naught is the force in vacuum, and it will be given by 1 by 4 pi epsilon naught q1 q2 by d square, and Fm is the force in a medium. It will be given by 1 by 4 pi epsilon q1 q2 by d square, right? So this epsilon is permittivity of medium, epsilon naught is permittivity of free space or vacuum, right? So this epsilon quantity is the variable which differentiates force between two different mediums. So epsilon naught permittivity, the name itself suggests, it is the tendency of a medium to permit the flow of charge in between in itself. Like you can assume that if two charged bodies are placed in vacuum, there is no intervention there. But if some other atoms and particles are placed inside those two charged bodies, there would be intervention from the medium as well. You would see the nearby particles getting charged and discharged. So there would be intervention from medium as well. So permittivity is how easily a medium permits the flow of charge or the force between two charges. How easily medium won't disturb the effect of charge inside is what permittivity is all about, right? So this ratio of permittivity of medium to permittivity of free space is called relative permittivity. So relative permittivity epsilon r, this is called epsilon by epsilon naught, right? So the relative permittivity is permittivity of medium with respect to permittivity of free space, right? So this is relative permittivity, and it is also called as dielectric constant, right? Which is represented by K. Sure. So if I can generalize this epsilon now, so epsilon will become what? From here, epsilon will become epsilon naught epsilon r, right? So let me put a general equation of force. So force will become 1 by 4 pi epsilon naught epsilon r q1 q2 by d square. So this is the force. Now we have considered the permittivity, relative permittivity as well. So if we are calculating for vacuum, the epsilon r will become 1. But for different medium, there will be different values of epsilon r, right? Okay. Okay, so we just talked about Coulomb's law, its discovery, the constant, Coulomb's constant. Now we know that force is a vector quantity, right? So whatever expression we wrote here, it's all giving the magnitude of force. Nowhere in that particular expression or somewhere I talked about the direction. So let's talk a bit about direction as well. Since force is a vector quantity, we need to take into account the direction as well. Okay. So just for a simple explanation, let's say there is a charge plus q, right? And let's say there is a charge plus q1 and plus q2, and these are 2 points separated by distance r, right? So now we can say that the force between these two will be k q1 q2 by r square, but this is the magnitude of force, right? Now let's say that if I want to know what force b is exerting on a and what is its direction. So the force we know, but direction we need to analyze. So these two are positive charges, right? These two are like charges, so they will repel each other. So tendency of B will be to repel A in this direction, right? And tendency of A will be to repel B in opposite direction, right? So let's say FAB is force on A due to B, right? So its magnitude will be what? Its magnitude will be K Q1 Q2 by R square. And for FBA also, the magnitude will be F Q1 Q2 by R square, right? But if we talk about direction, what happens is the direction is opposite. The direction of force of A on B and B on A, they are opposite. So vectorially, if I write, they are anti-parallel of each other, right? Right. So the magnitude is same, since Newton's third law says that equal to, there is equal and opposite forces between two charges. So whatever force A will exert on B will also exert on A, but directions are opposite, right? So this is what the vector representation of this particular force. Now let's generalize the Coulomb's expression in vector form. So let's say this is a plane, 2D plane. I'm just concerned about 2D plane as of now. There are 2 points. A, it has a charge Q1. There is a point B, it has a charge Q2. The distance between them is R, right? So let me connect this with this origin. So if I connect A with origin, let's say this vector is, this position vector is R1, right? If I connect B with origin, let's say this position vector is R2, right? So let's say that now I know what will be the force between A and B. So let's talk about force exerted by B on A. So force exerted by B on A will be K Q1 Q2 by R square, the magnitude, right? So can I write it like this? R21 square, right? So yeah, again, this particular thing, this is the magnitude is R, but vectorially if you see, from A to B, the position vector would become R12 vector, which would be R1 vector minus R2 vector. But from B to A, if you see, the position vector will be R21 vector, which will be R2 vector minus R1 vector, right? So force on A due to B will be K Q1 Q2 by R21 square. This is the magnitude of force. Now what I need is, I need to convert this force into vector form. So to convert any quantity into vector form, we need to multiply it with a unit vector, right? So let's multiply it with a unit vector. So unit vector in this direction is R21 cap, right? So now I can say that this force in vector form is given by this particular expression, right? Let's simplify this a bit. So you know, unit vector is what? Unit vector is a vector divided by its magnitude, right? So now FAB will be what? K Q1 Q2 by R21 square into R21 vector by mod of R21, right? So this becomes K Q1 Q2 by R21 cube into R21 vector, right? So this is force on A due to B. Similarly, if I talk about force on B due to A, what will change? It will be again same, Q1 Q2 by, let's say this will become R12 Q, and this will become R12 vector. Now what is the difference here? This is R12 position vector, this is R21 position vector, both are opposite of each other, and hence f of AB vector is negative of f of BA vector, right? Right? So we just talked about Coulomb's law in vector form. So let's say that there are two charges, Q1, Q2, and they are separated by distance d. So force on B due to A will be what? K Q1 q2 by r12q into r12 vector, right? And let's say if we are talking about d here, so this will be d12 and d12 vector, right? So this is the position vector, right? The magnitude of d12 is obviously d, and force exerted by A on B will be given by k q1 q2 by d21 q into d21 vector. So this is what Coulomb's law is, vector form, right? So d12 is what I just explained, that d12 is position vector of 1 minus position vector of 2, position vector of A minus position vector of B, something like that. So let's say this is d1 from origin and this is d2 from origin, so this will become d1 minus d2. So d21 become d2 minus d1, right? Okay, so yeah, let's solve a question on Coulomb's law, which we just studied. Right. So let's solve a question on Coulomb's law. So let's say there is a equilateral triangle A, B, C. Right? This is equilateral triangle. Ignore the shape, but yeah, this is equilateral triangle. So three equal charges are placed on the vertex of this equilateral triangle: plus Q, and plus Q. Right? Now, at the centroid of this triangle, we have a charge plus Q. Right? Let's say this point is O. Okay, this point is O. Now I need to find what is force on plus Q due to all three charges at A and B and C. All three charges at A, B and C, right? So this is the question. So we need to think on the direction. Then how do we start with this particular question, right? Yeah. So how do we approach this particular problem? First, let's understand the question. There is an equilateral triangle. Let's say the sides out of length L, L and L. Sorry, L, L and L, right? So now there is a charge placed at centroid of this triangle. Centroid, we all know that centroid is the intersection of all medians. So there is a charge placed at centroid, and we need to find the force on centroid due to this charge, and this charge. You know that this particular charge is in the vicinity of these three charges, so all three will be exerting a force. Maybe this will exert a one force, this will exert one force, this will exert one force. So we need to find the net force here, right? Okay, so let me redraw this diagram and start with the question. So the solution of this particular problem. Right, so this is L, this is L and this is L, right? This is plus Q, plus Q, plus Q. The point is A, B, C. So this is a, you know, the centroid and the altitude, they overlap. So yeah, this is the centroid and this crossing of this centroid. Yeah, so there is a charge called plus Q, right? So A will exert a force, B will exert a force and C will exert a force on O. So there will be three forces: force on O due to A, force on O due to B, force on O due to C. So force, we already know that force is given by what? Let's say it is given by K Q1 Q2 by R square. So we have charges already, right? What we don't have is the distance. So we know that we have, let's say this point is D, right? So this particular distance AD, right? So all angles of equilateral triangle is 60 degree. So this particular angle is 30, right? 30. So now I can calculate AD. AD will be what? AD will be AC cos 30. You know the cos ratio, right? So cos 30 is root 3 by 2 and AD is L. So AD is what? This particular altitude, this is root 3 by 2 L, right? So now what will be AO? So we know that this particular centroid will divide this altitude into the ratio of 2 is to 1, right? So if this is two part of it, this is one part of it, right? So AO ratio OD is what? 2 is to 1, right? So overall, if I say AO is what? AO is 2/3 of what? AD, right? AO is 2/3 of AD and OD is what? 1/3 of AD, right? So I need AO for, right? So I know the AO will be what? 2 by third of AD, which is 2 by 3 into root 3 by 2 L. So this is L by root 3. So this distance AO or OA is L by root 3. So by symmetry, we can say that BO and CO will also be L by root 3, right? So now I can tell the magnitude of forces from A to O, B to O, and C to O. So F on O due to A will be what? K Q Q by L by root 3 square, right? But is this enough? We need to have a direction as well. So now you can say that since all charges are positive, they'll be exerting a repulsive force between them. So force on O due to A will be in the exactly in this direction, right? Exactly. Let's say this is our axis, XY axis, right? This is direction. So negative Y, right? Force on O due to B will be exactly in this particular direction, right? Force on O due to C will be exactly in this particular direction, right? And all the angles between these three forces, they are 120 degree each, right? Because all forces are equal in magnitude, right? So this is what? This is FOA, this is FOB, and this is FOC, right? So now let me make it a bit simple for you. So FOC and FOB, let's take two at a time and then we'll go for third. So let me draw a clear diagram. This is FOC, this is FOB, and this is FOA, right? Okay. And this all angle is 120, and hence this will be 60, this will be 60, right? This will be 30, right? So we know that magnitude of all three forces are same. So FOC will have a component here called FOC cos 30, right? And FOB will have a component here called FOB cos 30, right? So these two components are anti-parallel, they'll cancel each other, right? So the component of interest is the sine component, right? So this, the component here will be FOC sine 30 and FOB sine 30, right? So now net force is FOA and addition of these two in this direction, right? So now let's remove all this. So net force is what? It is FOA minus FOC sine 30 minus FOB sine 30. And we know that FOA magnitude is same as FOB magnitude is same as FOC magnitude, which is KQQ upon L by root 3 square, right? So let's call all of these as F, right? So this is F, this is F, sine 30 is 1 by 2, this is also F, sine 30 is 1 by 2, so it is F minus F by 2 minus F by 2, and which is equal to 0. So this all three forces, they are actually counting to 0, hence net effect on this particular charge is 0, right? This particular charge is in equilibrium condition since net force acting on it from all directions is counting to 0, right? So we just found that how can we calculate a force on a point which is surrounded by multiple charges, right? So it is as simple as that, but we need to have concept of vector addition, the parallelogram law, the triangle law, which I could recap. Like let's say there is as of now, this I solved the question using the component, but this can be also solved vectorically. Let's say this is a FB vector, this is a FA vector, and I need to find the resultant force. Let's say this is FR is the resultant. So we know that by triangle law that FR magnitude will be given by under root FA square plus FB square. Let's say the angle is theta plus 2 FA FB cos theta, right? This is the way to calculate the magnitude of resultant force, and we can also find the direction of resultant force. So I think the direction of this is given by FB FB sine theta by FA plus FP cos theta. I need to recap this particular, yeah, but I think this is the correct one, right? So this is the triangle law vector addition. So now let me generalize all this. Let's say there is a system, right? Let's say there is a big system. It has n charges, plus Q1, plus Q2, plus Q3, 2 plus Qn, right? And now I need to find force on Qn due to all particular charges, due to all other charges, right? So I can say that the net force will be because of 1 on n, because of 2 on n, because of 3 on n, 4 on n, and so on. So this is the net superposition of forces which is acting on Fn, right? And these are all in the vector form of it, right? So we understood on how can we calculate forces and between different multiple charge bodies, right? So let me leave you in this lecture with a question. You can try it out on your own. So again, let's say we have equilateral triangle. It has charges like plus Q, minus Q, and here let's say it has again a minus Q, right? This is A, B, C. The distances are L, L, and L. So the question is, what is the net force acting on plus Q charge placed at A, right? So at this particular charge, what is the net force, right? You know that this B and C will be contributing to that force. So you need to find it out that what will be the net force, right? And we'll discuss this in the next lecture. Thanks.